Let's look at the properties of the power spectral density of a wide sensational random process. Well, of course, at this point, I should remind you, whenever we are talking about power spectral density, at least in the context of this course, we are talking about a wide sensational random process. Okay, so that is basically an indicator of the importance of wide sensationality, as I have mentioned in last week's class. Wide sensationality is quite important, maybe more important than strict sensationality because it's much more practical and it's much more useful. It's much more widely used in practice. Okay, so whatever we do here is in terms of spectral analysis, it all assumes the random process you are dealing with, x of t, is wide sensationary. Now, for such a process, the power spectral density is always non-negative because it's defined through the periodogram estimate, and the periodogram estimate is by definition it's a magnitude square of something, so it has to be non-negative. Okay, and the next observation is, although it's defined through a Fourier transform involving complex exponentials, it's a real function. Okay, let's see why that is so. Take the definition. Okay, the autocorrelation times e to the power minus j2 pi f tau d tau. Now, at this point, you have to use the identity of Euler. Okay, quite well-known identity, e to the power j theta for any theta in radians is equal to cosine theta plus j times sine theta. Okay, this is essential in complex analysis, and this is due to Leonhard Euler. So here, if you just plug this in, and theta here in our case would be minus 2 pi f tau, right? Therefore, uh, if you just plug this in this expression, you will have the autocorrelation times cosine 2 pi f tau minus j sine 2 pi f tau d tau. Now, where did the minus sign go? As you know, the cosine is an even function because cosine minus theta equals cosine theta, and sine, on the other hand, is an odd function. Sine minus theta equals minus sine theta. Therefore, the negative sign in the cosine disappears. I don't need it. And the negative sign inside the sine, I can take it out. And it appears here. Okay. So, furthermore, for a wide sensation random process x of t, we know that the autocorrelation Rx of tau is an even function. We know that Rx tau equals Rx minus tau, right? So cosine is an even function, autocorrelation is an even function, and sine is an odd function. What's an odd function? It's symmetrical around the origin. Okay, if you remember sine, it's something like this, and it's something like this, right? If you take this, it has the negative. If you take this, where is it? This is here. Okay, you take the negative values. Okay, so essentially the point here is if you multiply this autocorrelation, which is an even function, with an odd function, the product will be an odd function. Okay, it's like multiplying like x squared, which is an even function, with x, which is an odd function, which gives you x cubed, which is an odd function itself. Okay, even times odd gives you odd function. Now, when you integrate an odd function across the entire real line, right, like this one or this one, it will give you 0, right? Because the area on the right-hand side will kill all the area on the left half plane, right? Because this area equals this area, but it's negative. This area here is equal to this area, but it's negative, so they cancel each other out. So the integral of an odd function over the entire real line is 0. So this will not contribute to the integral. What will remain is autocorrelation times cosine 2 pi f tau d tau, okay? And the observation here is there is no j here, no complex unit, so this is a real function, okay? Power spectral density of a wide sense stationary process then is a real function. Furthermore, based on this derivation, this is an integral of an even function, and therefore it is itself an even function because, well, it's clear that if you plug in minus f instead of f, you will see that it will be inside the cosine, so it will not matter at all. It's either f or minus f. It will lead to the same value out of the cosine. So the result will be the same for f and minus f. That means the PST itself is an even function. Okay, next, the autocorrelation. Well, as we have seen, the PST is the Fourier transform of the autocorrelation. So the autocorrelation can be recovered from the PST through inverse Fourier transform. Okay, clearly so. We also have seen this when we discussed characteristic functions. And the next property, the area under the power spectral density gives the average power of a random signal. Okay, if you integrate the PST over the entire frequency domain, okay, because, well, you see, by definition, the average power of the signal is its magnitude square. Whenever it's random, it's the second moment, which corresponds to the autocorrelation evaluated at 0, which is equal to this expression, because as we have just seen, the autocorrelation equals this integral, and when you evaluate that tau equals 0, you just put 0 here. So this exponential term will be equal to 1. So this will be equal to the integral of the power spectral density over the entire domain. Okay, so in short, the area under the PST gives you the average power of the random process. Okay, and moreover, you can actually confine it to bands of frequencies. Let's say the power of random signal frequency band F1 to F2, you are interested in this because you are interested in this specific band. If you are, let's say you are designing a system that will operate in this band, and you are interested in the power concentrated on this frequency band of a random process, then what you do is you integrate the power spectral density on this interval with a twist. Here, if you remember, I had said that the PST is an even function. So this is the frequency axis. It's something like this, let's say. Okay, it's an even function. Okay, so the frequency band is here from F1 to F2, and you will have to do it on the negative side too. Now, what does negative frequency mean? It's an abstraction. It's not really a real quantity, but it's a convention of how we express rotations, let's say, because complex exponentials are involved. We end up with negative frequencies too, but they do not mean real vibrations in sort of negative sense. It doesn't exist in the real world in that interpretation. But essentially, you need to integrate the power spectral density both in these intervals, okay, from minus F2 to minus F1, and then F1 to F2. So that is the total power embedded in your signal in this band. But since we know that the PST is an even function, this area is equal to this area, so you can just write it as 2 times the integral from F1 to F2 of the PST.